Hello, welcome everybody. Good afternoon. Welcome to the Connections webinar. My name is Olivier de Moor. I'm Application and Sales Engineer at Connections, and I will guide you through today's session. So we have different participants today, both from industry and academic world with different backgrounds. And there are people that are already working with laser Doppler vibrometry, people that are quite new to the topic, and I made sure that this session is valuable for both groups. So the topic of today will be single point laser Doppler vibrometry, and with the focus on the different types and different technologies. So first I will introduce you to the basics of laser Doppler vibrometry, how laser vibrometry works. Then I will give an overview of the different single point systems. I will go a little bit deeper into the new QTec multipath interferometer technology. Then we will have a introduction about the OROS 04 USB analyzer, which will be used during the live demonstration. And before the live demonstration, there will be a short question and answer session already. So if you have any questions during the presentation, please write them down in the Q&A section next to the chat. And we will already address them before the live demonstration, and there will be a second Q&A session after the live demonstration. First, I also want to introduce Connections. So we are since 25 years the exclusive distributor for Polytech laser Doppler vibrometers in the Benelux and South Africa region. We are also exclusive distributor for OROS multi-channel data acquisition systems in Flanders and the Netherlands. And we are starting to work together with Spectra. They are specialized in high frequency exciters, calibration solutions, and MEMS testing solutions. So Polytech is a German company. They're located in Waldbronn, and they are already existing since 1967. So they have a lot of experience in the production of optical measurement solutions, but today we will only focus on laser Doppler vibrometry. There are different types of laser Doppler vibrometers. The single point laser vibrometer is just a point and shoot method. So you point your laser beam to the target that you want to measure, and you can get directly the vibration information of the point that you measure with your laser beam. With the scanning laser vibrometer, this is the same method, but now you use two steering mirrors to move the laser beam in X and Y direction over your surface, so you can visualize the deflection shapes of the vibration. With the microsystem analyzers, you actually implement a scanning laser vibrometer in a microscope to measure on very tiny objects like MEMS structures or biological tissues, and you can also visualize the deflection shapes of your vibration. There are some new developments at Polytech, both in meso and micro scale. So in the beginning of this year, Polytech released a new VibroScan QTec scanning laser vibrometer. And now there's a special add-on where you can actually extend it with a microscope objective to measure also on MEMS structures. So you can use the scanning laser vibrometer for big macro applications and now also for meso and micro applications. Of course, if you still want to go to the best specifications, small spot size, small spatial resolution, then the MSA 600 still outperforms for MEMS structures. And our latest MSA 600 now also goes to 8 gigahertz. So we also distribute OROS. So OROS is a French company located in Grenoble, and they're already existing for 40 years. And they are specialized in the production of high-end data acquisition systems for noise and vibration analysis. And there are two different product lines. We have the standard Teamwork platform, and we have the 04, which is a USB analyzer. So both power and data go through USB connection, while the Teamwork platform, they are standalone systems. They have internal calculation power, and they can be cascaded up to 500 channels for applications where a lot of sensors are required. Spectra is also a German company, and because we already have data acquisitions, we have sensors. Now we also have excitation methods, so they produce high-frequency exciters, high-accuracy exciters, also for shock applications, pressure, sound. They also provide calibration solutions, mobile calibrators, complete calibration setups, but also calibration services for any type of sensor. And they also have MEMS testing platforms, both for digital and analog sensors, and for R&D and production. So we as Connections, we also have our own expertise and the equipment, so we can also provide services and consulting ourselves. And this is then non-contact vibration measurements with our Polytech laser vibrometers. And we are specialized in operational model analysis, experimental model analysis, structural analysis, and so on. We also provide trainings, both for Polytech and OROS. We can also rent out systems, and we also provide calibration services through Spectra. So why did laser vibrometry become such a preferred tool? First, it's a non-contact method, so it's a non-destructive method of measuring vibrations. It also has no mass, so you don't change anything to the dynamics of your structure, and there's no additional damping or no shift in eigenfrequencies. You can also measure at all temperatures, so very hot or very cold surfaces will not have any influence on your measurement itself. You can measure from different standoff distances. This can be a couple of centimeters to hundreds of meters with our latest systems, and you will not have any influence on the resolution of your vibration measurement. You can also use scanning, mirrors, or fiber optic lenses to reach difficult to access points. And the laser beam itself is in terms of microns in diameter, so you can very accurately target your laser on a certain point on your object. Our latest systems are also equipped with an autofocus functionality, so where the system actually finds the best focusing position for the certain standoff distance. So now I will show you a video of how the inside of a laser vibrometer looks like and how the basic principle works.
Laser vibrometry uses the Doppler effect to measure vibrations. If light is scattered from a moving object, its frequency is changed slightly. Within a Polytech vibrometer, a high-precision interferometer detects the minute frequency shifts of the backscattered laser light. To achieve this, the interferometer splits the light into two parts. The so-called reference beam is pointed directly to the photodetector, while the measurement beam is incident on the test object where the light is scattered by the moving surface. Depending on the velocity and displacement, the backscattered light is changed in frequency and phase. The characteristics of the motion are completely contained in the backscattered light. The superposition of this light with the reference beam creates a modulated detector output signal, revealing the Doppler shift in frequency. Signal processing and analysis provides the vibrational velocity and displacement to the test object.
Okay, so we have two different types of lasers for different applications. We have the helium-neon laser with 1 milliwatt output power, and this is the laser with the smallest wavelength, so also the smallest laser spot and best resolution. But this is only the case when we get enough light back, so it can be possible that you need some surface preparation or you have a very shiny object, and then you will have good resolution. It's also possible to use this laser to measure through transparent media like water. The second laser is the infrared laser, and there we have 10 milliwatt output power, so 10 times more power. And this is because infrared light gets absorbed by water, so also by the human eye, and therefore we can go higher in output power but still stay eye safe. So we send more light to the structure, we also receive more light back. So this means we can measure over larger distances, and we can measure even on rough, dark surfaces, which are not reflective at all, and still get good signal. The higher wavelength also makes it possible to measure higher velocities up to 30 meters per second. So we have different types of single-point laser vibrometers. Our most basic one is the EVS 500 or the industrial vibration sensor, and this system is specifically made for implementation in production lines or quality control end-of-line test setups, and it's easily integratable in your own monitoring systems or data acquisition systems. Then we have the VibroGo system, which is our portable system. And this has the same methodological properties, but now it's more user-friendly. So it has a touchscreen where you can configure all the settings, and it's really, really portable to go on the field. And then our most advanced platform is our VibroFlex platform, which consists out of a controller and a sensor head and a different sensor head for each application. So the VibroGo has a touchscreen where you can configure all the settings, but you can also view the live data, and it's even possible to record the data on the system now. So we can record the data and look at it on the system, or you can upload it to your computer afterwards and view your measurement data this way. It's a lightweight system, it's outdoor-proof, and it's also possible to connect wireless with your laptop or with a tablet. The VibroFlex platform consists out of the Connect controller and then one of the different sensor heads. So the Neo is our standard helium-neon sensor head with autofocus functionality. The compact sensor head is also an helium-neon sensor, but now it's possible to integrate a camera in the compact small head, so you can very easily target, very accurately target on your object. And it's even possible to attach a microscope objective to measure on tiny objects. The fiber system it can be used as both a single point system or a differential system. And if you use it in differential mode, you actually measure the distance between 2 points. So this could be useful if you want to isolate, for example, vibrations of a smaller component on a bigger vibrating structure. The QTec sensor head is our only infrared sensor with the QTec multipath technology. This technology I will explain later during the presentation. So if we compare the different single-point systems in terms of frequency, amplitude, and resolution, we see that the VibroFlex actually outperforms the IVS 500 and the VibroGo. So we have the largest measurement frequency, largest amplitude, and the best resolution with the VibroFlex. It's only possible to use the infrared laser in combination with the VibroFlex system, and with this infrared we can also measure larger distances, now up to 300 meters. So before I explain the QTec technology, I first want to introduce you to speckles and dropouts. So we are using a coherent light source. This means that there's only one wavelength. And the laser spot will have a certain diameter, and this diameter will probably be bigger than the surface roughness. So there will be backscattering of the laser light in different direction, and since the laser light has only one wavelength, there will be negative and positive interference. If there's a spot with negative interference, there will be a dark speckle, and there will be little or no information coming back to the photodetector. If there's positive interference, then there will be a lot of light coming back, so a lot of information. So if we have a friendly surface or a reflective cooperative surface, and there's such a dropout, then it will probably stay above a certain threshold, and you will still have a nice vibration signal. But if you have a dark, rough surface, and there's such a dropout, then it will go below this threshold, and you will have a high frequency peak in your time signal, which will also result in a high frequency peak in your frequency domain. So how does QTec work to overcome this? So here you see such a speckle pattern, typical speckle pattern, and there will always be some lateral movement of your sensor head or of the object, which will cause a change in speckle pattern. And this will cause dropouts in your time signal. With QTec, we're going to look from different perspectives or slightly different angles to the same point. And now in each detector channel, there will be a different speckle pattern. And if there's a dropout occurring in one of the different detector channels, in the other two channels, there will be no dropout. So this will then be combined to a completely clean dropout speckle-free signal, which is much more reliable than a single path detector. Okay, so before we go to the live demonstration, I also want to introduce you to the O4 analyzer from Oros. So both data and power go to the USB-C connection to your computer. It has the same high-end metrology as the Teamwork platform that I showed you before. Now, the only benefit of this system, one of the benefits of this system, is that it now goes up to 100 kilohertz. And that is quite a good fit with our laser vibrometers because we often have high frequency applications, and this is quite handy tool. So you can connect one vibrometer, multiple vibrometers, or a vibrometer with different sensors. This system also uses the standard NVGate platform from Oros, and it can also have the additional software packages like modal analysis, rotating, and so on. Okay, so we are already at the first question and answer session. So I see there are no questions yet. So if you have any question, please write them down in the Q&A section. You still have some time during the live demonstration to think of questions, and then I will answer them after the live demonstration. Okay. So for the measurement setup that we will show later, there will be a metal plate which we will excite with a loudspeaker excitation, and we will send a multi-sign signal from the Oros analyzer to the metal plate, and we measure with our laser vibrometer. This will be a helium-neon laser vibrometer, an infrared laser vibrometer, and an infrared vibrometer with QTec technology. And the output, the vibration output of the laser vibrometer will then be connected back again to the Oros analyzer. So we will excite and measure both in the Oros platform. Okay, so now I will go to the live demonstration. Okay, so we will perform our measurements today in NVGate, which is the software to operate Oros systems. We will select the O4 now, which is the 4-channel USB analyzer. And we will, you can also open NVGate just for looking at measurements, but now we will open a new project. For the webinar, you can also open recently used projects, or you can load measurements. You can choose the project name, so that is the description of what you will be measuring. So for now it will be the webinar for the single point measurements. So then we start, and the first thing we need to do is to configure and select the inputs. So depending on which sensor or transducer you are using and which physical quantity that it will measure in, you can set it up all here. Also the sensitivity. It's also possible to select transducers that you have already loaded in your database. So for the vibrometer, we will use a velocity sensor. So then the sensitivity changes into volts per micrometer per second. And then depending on the range on the vibrometer is set on 5 millimeters per second. So if we calculate that, that will be 400 to the 10 times minus 6 volts per micrometers per second. It's also possible to change another coupling like ICP, DC, AC. You can change the sampling frequency. It's possible to record signals. You can check the box on the down below. And yeah, there's a lot of things that you can set up already here. So the next thing that we will do is we will configure an output generator signal that will be sent to the loudspeaker. So it's connected through a BNC connection. And we will choose a multi-sign for this so that we excite all the frequencies of the frequency spectrum. So we connect the multi-sign to the output 1. And here we can choose the lower frequency, the upper frequency, the frequency resolution, and the number of FFT lines. And it's important that the number of FFT lines is chosen the same as the resolution of the FFT itself. So here we going to lower the resolution a little bit so that we have more frequency lines. And we will also make it a little bit more amplitude. So the max amplitude we can generate with the O4 system is 2.5 volts. And that will be sent to the loudspeaker. Then we go to the output settings, and here we will make it synchronized, linked to the measurement run. Otherwise it will always be on. So now the generator signal will turn on when we start the measurement. Then there are some additional settings that we can configure, but that's okay for now. And then we will go to the results tab. So here we can actually configure what we are going to visualize and what we are going to measure. We can show the triggered block, the average spectrum, the frequency response function. For this measurement we will only show the average spectrum because we only have one sensor connected, and then we can go to the FFT settings. So here we can already adjust the frequency lines to the same number of lines that we have used for the generator, so that's then we have a resolution of 1.5 Hertz. Here we can choose the averaging, so we use 10 averages, we make a linear averaging. So now we have completed all different settings. So we have an excitation signal going to the loudspeaker. We have the measurement channel connected. So now the only thing we need to do is the setup itself. So what we will do, we have a loudspeaker box where a metal plate is hanging, and we point the vibrometer there. The vibrometer is connected to the Oros analyzer, and the Oros analyzer sends a signal to the loudspeaker. Okay, so now we will perform the measurement. So you will hear the multi-sign signal going to the loudspeaker, to the object, and the vibrometer is measuring on this point with 10 averages. So now we did the measurement with the QTec technology on, so with the infrared laser and the multi-channel detector technology. So you see as expected, the measurement looks quite nice. You can clearly see the resonance peaks. And now we will see how it behaves when we give a swing to the object. So because now it was stationary, but we want to see what happens if the object is moving. So now we will give a swing to the object while performing the same measurement. So the object is clearly swinging. There's a difference in distance to the laser. So we expect the measurement to be more difficult. And we see that indeed the signal gets more noisy, but you still can see the resonance peaks coming into the signal. So the next step is to repeat this, but now we turn this QTec multi-channel interferometer off. So we do a measurement with the same sensor head, but we can turn this QTec technology off as a demonstration purpose. So if we repeat this measurement, we will do exactly the same, and we see that directly that the noise floor of this measurement without QTec is a lot worse than before. So it's a lot higher noise. Only the very high peak comes out of the signal. So we will also save this measurement so we can make a comparison between those two measurements. So this one is the QTec off. And if we overlay those plots, so we can put them over each other in the software, we just need to swipe them on top of each other. Then you see clearly that with the QTec on, the green one has a lot better noise floor, even when the object is moving. That with that certain amplitude, you get much better results. Thing we will do is we will test also this with our helium-neon vibro go system. So this is with a 1 milliwatt output power red laser, and we will see how this one reacts on the same conditions as with the infrared system and the infrared system with QTec on. So now we connect the vibro go system with the analog output to the Oros analyzer, and we repeat the measurement without movement. So this is just a stationary movement. So now you see the red laser, and if we look at the results, You see, yeah, it's similar to the QTec because it's a shiny cooperative object, so you can expect good results. Okay, we save this one also so we can compare it to the other measurements from before. Now we will do the same measurement again, but we will make the plate swing again while doing this measurement, so that you have again the large displacement moving in plane direction and out of plane direction. And now we see with the helium-neon laser that you don't even see the vibration peak, so you don't even see the resonance peak because it's just in the noise floor of the measurement itself. So we also save this so we can compare it to the previous measurements, and we can make a comparison of all the different results. So what we will compare now is the Vibro Go with the movement of the plate and with the plate stationary. So to see the difference. So as you know, the stationary measurement was quite good actually. So here the noise floor is much less, and with the large movement you can actually measure nothing. So with helium-neon lasers it's actually very difficult to measure on moving objects or objects with large displacement amplitudes. Then infrared becomes really a handy tool. So if we compare now the measurement with no movement between QTec and helium-neon. So the green one is the VibroGo, the helium-neon one, and the orange graph is the Vibroflex QTec. And you see that even on the stationary part, the infrared laser with QTec technology still gives better noise floor than the helium-neon system. Because it's just, even if the laser has a smaller wavelength for the helium-neon, there is just more light coming back to the infrared one, and that's why the noise floor is better for the infrared one with QTec. And if we compare the QTec off versus the VibroGo versus the QTec on, you see clearly the difference between helium-neon, infrared, and then QTec even gives way better noise floor resolution. So that's a little bit the conclusion that we can get from this measurement of the three different sensor types that we have. So if you have very cooperative objects that are stationary, then a VibroGo is really good choice. If you have difficult objects like rough surfaces, dark surfaces, infrared is very good. And when you have large amplitudes or in-plane movements, QTec is really the best choice that you can make. Okay, so now we have both seen the theory behind the different technologies, and we have also seen the live demonstration of the different systems. So I will go to the Q&A now. I've seen that there are by now some new questions. So the first question. Wait, there's also a question in the chat. Yeah, I saw also a question in the chat. Okay, let me first do the questions in the Q&A section. So thank you, Oscar, for the question. And the question is, the frequency of the LDV is limited by the sampling time of the OROS data acquisition system, for example, OROS 04. So this depends. So our systems can now have both analog and digital output. So if you have the digital output, actually the bandwidth of the laser is limited by the option by the configuration that you per case. So we can have, for example, with the VibroFlex system, we can have up to 24 megahertz. With the VibroGo, we can have up to 320 kilohertz. So that's the limitation of the systems. If you use a data acquisition system, like an oral system or any other data acquisition, then most of the times the bandwidth will be limited by the maximum bandwidth or sampling frequency of your data acquisition. But this is only when you use the analog output of the laser vibrometer and not the digital one. So I hope this answers your question, Oscar. Okay, I have another question. From Zahir Essa. Hi, you mentioned option to record directly to the VibroGo. Can you record at full sample rate, and how large is the storage? Period of recording with the highest sample rate. So indeed you can indeed record at the highest sampling frequency. That's no issue, and then you can record several time blocks, and indeed the time is depending on the sampling rate. So, but what you could do, you could measure multiple blocks. So you could say I want to measure 10 blocks, and then you can stitch them afterwards after each other. So that's a possibility. That's also an application I already performed once, where I needed to do a 30-minute measurement on the VibroGo. And then another limitation might be the storage on the system, but that's about 13 gigabytes. So you can measure for some periods of time, and then you can afterwards put the data, for example, on your laptop or on your computer, and then you can start over again. So then the system is empty again. So I hope that that answers your question. And then we have one question in the chat. Good day. Can a vibrometer be used to measure a 3D surface structure or roughness? If so, what XYZ resolution could be achieved? From Amit Sharma. Thank you for the question. Yeah, that's actually a good one. So in our scanning laser vibrometers, we have the possibility to have a high precision geo scanner also. So when you make your grid for the scan that you want to measure all the points, you could also do a distance measurement for each point, and there you could so then you can have a complete 3D geometry of your structure. If you really want to have the surface roughness, that's not really the purpose of a laser vibrometer. There are other systems like white light interferometers to really have the topography of the system, of your object. Okay, so let me know if that answered your question a little bit. But if you want, I can send you some more information afterwards also. So any more questions left? Okay, I see. Okay, another question from Oscar. Thank you, Oscar. To measure a surface, not point, could the LDV do a grid or random locations on the surface? So yes, our scanning laser vibrometers, they actually use two mirrors to steer the laser beam and do a measurement point by point of an entire surface. And afterwards, you have all the information of the different points. You need a reference sensor or an excitation signal for that. And then you can actually visualize the vibrations of the entire surface. But if you want, I can send you some more information about that. Okay, so any other question? We still have some time. Okay, then I think this was all for the questions. Then I would like to thank you all for the participation of the webinar and also for the questions. And if you have any further questions about product information or consulting or any other, if you want to have a live demonstration or a virtual demonstration, please let us know. Then we can organize this also one-on-one and discuss which solutions would be best for your applications. Okay, then I wish you all a very nice rest of the day. Bye.